Thank you. As you can see, Ian Whiteway, I worked this year at St Andrew's Cathedral School, right in the middle of Sydney. Last year I was at UNSW as the visiting teaching fellow, and before that I was teaching online with Aurora College. The topic I've chosen comes from out of a couple of the contributions from the workshop in December last year, which was when we were mainly online. And I found two of the contributions there extremely helpful and things I could apply at high school level, and hopefully you'll see how they can apply at tertiary level as well. I wouldn't claim to be on the same level as those presentations, but I think at least if I can keep those ideas going, that's a useful thing. One of them was by Chris Tisdell, and he spoke about this idea of looking first. And he gave an example, the other one, Merrill and Horrocks, on the importance of students having good mental models. And that's the question. And what I'm going to mention, particularly with the view of the theme of today, is how assessment can be a tool in promoting both of those worthy goals. That's promoting good mental models and looking first. So first of all, looking first, we had that example last year of solving 1 over x minus 1 is greater than a third. And what was drawn out of it is if you gave that to a lot of students, they would then go into algorithm mode and they would try to consider the case where 1 over x minus 1 could be negative, and they look therefore at having to adjust or flip the inequality sign and so on. And the point was made, well, if you think about the question, you wouldn't really go there because you can see that x minus 1 must be positive because 1 over x minus 1 is greater than a third. What I tried to do then is to think of other examples like that, and I'm sure there are many out there, and I'm just going to really click through a few of them. Very simple one there, of course. That's probably going back to early high school, if not lower. But students out there who go into algorithm mode and they would do things like multiply the 6 by 24 and then the 24 by 1 and the 6 by 7 and come up with something really unnecessarily complicated when they should be able to see how simple it is. This one, odd functions, realizing that something like that turns into 0 because of the way an odd function is. This one comes up in the HSC sometimes, knowing that once you've got a circle, you can just use the area formula of a circle or a cube. This one, something like came up in one of my classes this year in an exam, and students trying to simplify the fraction rather than just realizing you can solve the numerator, but then you must test that in the denominator to see if it won't lead to a 0 or a square root of a negative or something like that. This one, I've seen this in university type tutorial questions. Students not always thinking that the object obviously will reach the room temperature, but it does assess something. Ones like this, again, thinking about a graph would quickly lead to a solution, just bearing in mind where one of the functions wouldn't exist or would not be defined, I should say. Again, ones like this, realizing it's got to be positive on one side, so therefore it's got to be positive on the other. So lots of examples like that. I'm sure there are many, many others, but as I've been teaching for a long time, I'm starting to realize that part of my role as a maths educator is helping students to see those sort of things. And how do you get them to see things like that rather than just persist in doing the algorithmic process that may eventually lead to an answer, but is very inefficient. And thinking about that, obviously modeling them and putting commentary in and explaining why you're doing things. So when they go and look back at it, it's often those informal notes that can add to the lecture notes or to the class notes that are the thing that's going to help. Assessing the better methods, finding questions and ways that will actually make them use the better method, either explicitly or by putting a bit of time pressure on, that if they don't see that they're using an inefficient method, it's going to actually have some consequence. That's that idea there, that they can still get full marks, yes, but the more efficient method is going to save them time, and they may have to explain, write a sentence or two about why they were able to do what appeared to be a shortcut, but in fact was mathematically legitimate. And then the idea that once questions like that become part of the repertoire, then they feed their way into exam questions or assessment questions. They feed their way into the bank of past questions. Then they enter the mainstream and students learn to use them. and start using them as a standard response. So just a few ideas then on that look first idea. And as I say, they'll adopt them once they enter assessment world, so to speak. The other thing from last year was the idea of looking, good mental models. And that really resonated with me. I've only taken, I think, some really basic things out of this, but the idea that students have either memorized procedures or no mental models at all in their brain. A few years back, I taught a year 7 class, and part of the program was you have to show them about errors in calculators. All right, put in the square root of -4. And this girl, perhaps 12 years old, looks back at me almost expressionless. That's 2i. So we're talking someone who's just started high school. So obviously, I think the tutor said, you follow this process, you get this answer. There's no mental model at all there, I think. There's only a process. And then once you just look at surface features, and the difference in strong students, as was mentioned, this is just quoted from last year, strong students have more detailed mental models. The weak students just function on a very surface level. And these are the students, some of them who come through to university without adequate mental models of what they're doing. They'll have processes and they'll end up in the numeracy class, and it'll be hard to help them improve. And at this point, I found so helpful about it's almost impossible to fix a faulty mental model. And I've been there in classes. You're trying to show a class a proper structured way of doing a problem, a way that you know is going to help them when they encounter a much more complicated version further up high school or beyond. But I know this quick way. I'm going to do it. My way is faster than yours. And as a younger teacher, you perhaps try to shoot it out with them almost. Yeah, you say, well, no, my method's better, and so on. But I realize more and more, as it says, you need to help them see the faults or the inadequacy in their model. And that becomes part of the art of an educator, is to show, all right, well, you do have a model and it appears to work, or a process that appears to work for some simple examples, but we'll try it on this. And you need to have more immediately available, those sort of ones that are going to show the problem with that, whatever field of maths it's in. So they appear to have a method that gets the right answer, and they're reluctant to abandon it, even though you can see what's over the hill. You can see that they're going to be solving a harder equation where they have to do the same thing to both sides of the equation, not magic tricks is what they're used to doing. And I'm going to move fairly quickly through the rest. I know that lunch is sort of around about now, but there's plenty of examples there, and I hope at least they'll illustrate that. And I'm sure you can add many of them from the work you're doing. So these are examples where students, from my experience, have no mental model or a defective one. Some are slightly amusing towards the end as well, I think. This one, multiplying decimals or multiplying any numbers by powers of 10. The ones out there, just stick a 0 on the end to multiply by 10, stick another 0 to multiply by 100. But yeah, what happens when there's a decimal? And then dividing, well, you could sort of cross them off. But again, once you hit decimals, the model's not going to work. And again, I'll just click through those, but they're in the record of it. Okay. Another one, algebraic fraction equals algebraic fraction. There's this mysterious process called cross multiply. And it's almost like an escalator system. Sort of the denominator of one goes sliding up to the other one, and the denominator of the other one goes slides up to that. And of course, we probably all do this as a shorthand, but we know why we're doing it. And it works. And yeah, my tutor taught it to me. We get this sort of thing back, the high school tutor, I mean. So I had to learn, how do you counteract that? Well, something like fraction equals fraction plus integer. Oh, they don't know what to do with the integer. And then they start to see the model is inadequate, and the student next to them, and that power of the peer success is very good. If they see the student next to them getting it right, that's more powerful than the teacher told me it's wrong. Oh, my friend used a better method and it worked. Swap side, swap sign. Something jumps over the equal sign and somehow it changes sign. Of course, we do it all the time. We say, let's move everything over to the left-hand side of the equation. And we know what we're doing. But the further down you go, the less clear that becomes. And for some students, it's just a process that somehow leads to an answer. And I'll just click through that. Solving equations by trying out values. Well, in a way, it's good. I mean, the fact they can substitute in properly is a great thing. But for some, they don't get past that. It becomes a routine. And the working out consists of trying this, trying this, trying this. Well, it's not mathematically wrong. But again, you have to find ways of leading them to the fact that it's not adequate and it won't take them very far. And, putting in an answer that's not an integer would be one. A more fun one is an equation you actually simplify it properly and you get x equals x, and then you have a multiple choice, and the answers, the first one will be something, I'll try it out, got it right, but the next one might be all even numbers, then all numbers, and so on, and they can't do that by trying it out, and they've got to reject that. This one I saw perhaps even at university level, not appreciating, so I can read it from there, can't I? Not appreciating that an additional independent equation is needed for each additional unknown. So if you have x equals something, one equation is enough, but once you have x plus y, you're going to need two or more equations normally. And students with matrices, they feverishly simplify them away, and finally they realize they're going to need a parameter, in the solution, but they don't always have the model that says that we don't have enough equations to solve these, and therefore a parameter, we're going to end up with it anyway. And then perhaps not even expecting that is the impression I get, because there's not a mental model of we need one more relationship each time to get another unknown. Some others, dividing or multiplying the numerator, and just one of that. So I do have an example there. This sort of thing, 2 over 2x plus 5. Sorry about the small size of that. You just cancel the 2 and the 2, and you end up with that. Again in your numeracy units, I'm sure you've seen this one. Cartesian axes, where the first unit is half a unit, and then all the others are 1 unit. They just sort of number them 1, 2, 3, and there's no mental model that equals space, and equal space means an equal value. Again, through setting other examples that can be overcome. This one, not realizing there's a difference literally between negative a and a. And you have this thing where you might have 5 minus a, and you subtract 5, and somehow you end up with a because the negative sign gets lonely and disappears. And I've taught in more than one country, and this seems to be a problem everywhere. There's no concept that negative a is a different thing to a. It could be, yeah. I think I've got it there. Yeah, lonely. Yeah.
A is always positive too. That's another.
It could be. Yes. The idea of when you subtract a negative, what does it actually do? Well, there's a process, but do they actually have a model? Or, as I say, negative x equals 3. Well, somehow the negative just flips over the other side, and you get x equals negative 3. But again, there's no model of what's going on there. It's a process without a concept, without anything that undergirds it. Yes, this one. Areas, volumes. There, a lot of people out there thinking that 1 square kilometre is 1,000 square metres. And another teacher gave this example, and I'll see if this link works. Get the thing to go to the right spot. Going to work. If not, I'll just summarise it. It was here we go. It was a report about the civil war in Sri Lanka, and near the top it says that the army says fighting is continuing as the rebels hang on to less than 1 square kilometre of jungle in the north of the country. But if you scroll down further, you'll find, I can get the reference, that they were actually holding on to 800 square metres according to the report. And of course, you do the maths, defending less than 30 metres by 30 metres would seem to be a very difficult task. I mean, not to make light of something that was a very terrible situation, but it is in there. I can't see the figure, maybe one of you can, but it actually does. It refers to 800 square metres. So that the reporter there, or whoever edited it, as we're finding out about editors this afternoon.
Third one down now.
Yeah, okay.
Third paragraph down there.
Yeah, so there's a concept that 1 square kilometre is about 800 square metres. So you can see that there's not a model there. No one's taught them it's 1,000 metres by 1,000 metres, and then you just do the mathematics. Okay, let's see if I get back to where I was. This one. And this one? Yeah. Okay. Binomial products. Again, you have attempts to make a telephone exchange, or if any of you have been in a sleep study where all the wires go everywhere, so you get the first two and just wire them all up. Well, that's good. I mean, it does lead to the right process, and there's FOIL, which again is probably a useful way of remembering it. But at university level, they're going to perhaps be doing a binomial times a trinomial, and the wiring's getting very complicated if you're going to try doing it like that. There's no real mental model like you've got a rectangle and you've got x by x and 5 by x, and you break it up and you model it in some way. So again, students are not really keyed into what they're actually doing. They just make the telephone exchange or just do everything and an answer pops out. There's no model. And again, it's going to, if they try to do higher level things with trinomial times trinomial or whatever it is, it's not preparing them for that. Yeah, okay, abstract calculations. I'll just explain those ones very briefly. One of the fun things I've done, although I haven't been able to do it for a few years, is around about the 1st of April, give students a question where they've got to do a scale model of the A380. And I look up the proper dimensions, and it's a 1 to 70 model, and you start off with the length of the aeroplane and the width, and you have 5 actual lengths. Then you make the other 5 quantities, things like the number of seats, number of windows, and you end up with the number of wheels, and you end up with a plane with 0 point something wheels, because they just divide everything by 70. And then you see some of them right at the end, and you actually see them go back and fix them, which is really a wonderful thing to see. But there's no context for what they're doing. They've just got into an algorithm mode, and there's no concept. It comes up in our other areas. I think students who are inland, and I've taught a number of those, tidal situations, the idea that the tide is gradual, there's no concept. Another school, we had a question with a fighter pilot who was flying along. He ejected his seat, and then he went to the top, and then he started going down and put the parachute on, and they had to draw a line graph modeling that. Well, all except 3 students, I think, had the pilot doing this at the top, which is quite scary. He's going up and then suddenly, almost immediately going down, which means his stomach probably went somewhere. Sorry, at lunchtime to bring that up, but the point is that there's students out there without a concept of what they're doing. There's no model, and again, algorithms and processes will only take them so far. And as I mentioned there's cases where planes have run out of fuel and things like that, where these things actually really do matter, that people have a realistic idea of what they're doing. I mean, when they're refueling it. Yeah. Okay, nearly there. And this one I've actually seen, and you'd be surprised where I saw it. I won't say where I saw it, but a student who substituted in infinity into a quadratic equation, and I had infinity squared, which does say something about a mental model. It's obviously a very extensive mental model of some sort. I guess the solution there might be ask them to put infinity and then infinity plus 1 on a number line and see what they might do. All right, just to conclude, because I know lunch is close. So getting students to replace non-existent, inadequate or defective mental models is no easy feat. And as was said last year, you can't just tell them to change their thinking. Particularly younger people don't like changing their thinking, and they want to sometimes repeat all the mistakes of history, which is sad. But if you can help them, though, to see that their model is inadequate, and often that's by setting a question and calling on your repertoire of mathematics education to help them see there's a problem they can't do as well or they can't do at all, that's a big step forward. And then showing superior models, because then they're ripe to listen to that explanation, is part of the solution. Assessment, though, can help with this, because under maybe a small stakes assessment, they could start to see that their model won't necessarily work, and they can see that their peers are doing better. But then when it gets to the ones that really matter, hopefully by then they've sorted that out. And it really also behoves us to set questions that require them to go beyond basic models or inadequate models, or explain what they're doing to show that they're not just doing an algorithmic thing, whatever topic or whatever level that's on. Teachers or academics will definitely have the ability to do that sort of thing. So assessment then could help in both these areas, looking first and also adopting good mental models. It could help by giving students the incentive to try the better ways. It could give them the incentive to start to jettison and adjust the ineffective ways. And so I think a small contribution, but hopefully I'll keep the pot boiling on both of these, because they're, I think, both really helpful things I find about getting the mental models right and looking first and helping students to see as many ways as possible where they can look first, not to take a shortcut, but to actually go in a more, more effective and more efficient direction.